you know the enemy, and you know yourself, you need not fear the result of 100 battles. Sun Microsystems 𝓁𝓧. As part of my arbitrarily selected life purpose of heralding in the age of effect, and thus despoiling the ancien regime of asynchrony, I will make you a promise from scratch. And to take Mr. 𝓁's advice here, once we can fully grasp promise's inner workings, we can then fully grasp it by the throat and hurl it back down into that sulphurous pit from whence it came, callback hell. And it is precisely there that we will begin with the callback, or the continuation, sometimes referred to as a handler. Long before promises skulked about this earth, we programmed asynchronous JavaScript with continuation passing style. Let us look at a brief example. Let's start by naively reading a file. First we'll import read file sync from Node, and then we can just straightforwardly read this book I found online into memory. And lastly, we can log it out to the console so we can absorb its knowledge. And let me also log something before we get started, just so we can get a sense of the program flow. I will now run this file. Alright, so first it printed out, here we go, and then it read the contents of the file and printed them out. Consequence-free power, Eye of Horus, yada yada, axe, scarab, vulture with, what is this? That's great. So this clearly works. It reads our file, it has a nice linear structure to it. And yet we would never want to write this code in a real system because this line here blocks our only thread. And this is because JavaScript consists of one main thread whose job it is to work its way through a task queue comprised of different tasks. It dequeues tasks from the front, runs them to completion one at a time, and then dequeues the next task, running it to completion, so on and so forth. The problem with our example here, however, is that task 1 is going to spend all of this time waiting for a blocking disk read. This I/O operation is handled by the operating system and therefore has nothing to do with JavaScript, so it's sort of silly that we're waiting for it to complete. But if we did not block here until this operation completed, then how would we be able to use its result in the remainder of our program? And this is where, of course, callbacks and continuations come into play. In regular direct-style programs, the continuation is merely the remaining lines in the file. In our case, this consists of logging the contents of the book. But what if we instead reified the continuation of our program into a first-class function? I'm going to import read file, the asynchronous version. Then I'll copy-paste the line where we read the file. I will delete the assignment because we will no longer be blocking, and I will delete the sync postfix. And now we will explicitly pass the continuation of our program as a function, which takes the book as its second argument, the result of that read file operation, and then I will copy and paste the console log, and then I will delete this expired comment. So now let's do another little ASCII simulation with our new asynchronous callback-based implementation. There is still the main thread processing a list of tasks. It pulls off the first task, which will be this file, and then when the runtime comes across this call to read file, instead of actually performing the I/O operation in the runtime and blocking, it instead hands off this responsibility to the host environment. And here there might be a pool of worker threads that might each be in parallel performing some kind of read operation. So our read-𝓁𝓧𝓅 operation will be kicked off immediately. And yes, there may be other I/O operations happening in parallel, but then the runtime does not wait for this process to finish. It would continue with the rest of the file. And so maybe we log something out, and that would happen immediately while the file is still being read in the background. And then this task is completed. So while 𝓁 is still being processed byte by byte, the main thread can dequeue task 2 and start working on that. Perhaps it manages to work its way through a couple of tasks, and then at some point, our 𝓁 operation will complete, that worker thread will be released to do some other work, and our callback will be enqueued onto our task queue. That would be this function here, getting called with whatever the contents of 𝓁 are. So then task 4 would run, and then finally our callback would be queued and run, and we will see our little message, gain the ability to talk to birds, and then later die a slow, agonizing death. Let's see if this actually works. I'm going to delete my comments, delete some of this stuff, steal my console log, delete, and now run the program. And as you can see, first it said, here we go, and then, before ever logging consequence-free power, it logged file over. That's because all read file does is delegate that I/O operation to the host environment, which will later re-enqueue the called callback onto our task queue. And now that we've embraced asynchronicity, we could easily read another file I've downloaded from the internet. And while our JavaScript code still executes on the same single main thread, the underlying I/O operations, the file reads, will, assuming we're working on a multi-core machine, run in parallel. So let me just run this file one last time. And here we have our results. First, here we go is logged. Then our non-blocking file read operation is kicked off. Then here we go again is logged, our second read file operation is kicked off, and then file over is printed. And then at some point in the future, the worker thread enqueues this completed callback, and thus the book of 𝓁 is logged. And then later on, everybody poops is also logged. Just to be safe, I will not read that aloud. So where this callback approach falls apart is when you want to sequence multiple operations one after the other. Let's say we only want to read poops if 𝓁 succeeds. Let me rename this, and then we'll say first we read 𝓁, and then we read poops. And then let's say we want to gzip their contents together. So we'll import gzip, jump down here, and then we can concatenate the contents and compress them. Then we'll log that we've compressed them. And then finally, we can write the compressed contents to a file and make one final log. Let's also import write file, and now we can run our program. And we will see that we read 𝓁, we read poops, we compress them, and then we write them. And we can confirm that this indeed has been done. There is our freshly gzipped file. Let me close out the terminals. And now we can bear witness to what is known as the pyramid of doom. When you code with explicit callbacks and you wish to chain multiple sequential operations together, your code is continuously indented further and further from the left-hand margin. We now reside in callback hell. We have Hadoukenized our program. And so it was out of a noble desire to assuage this syntactic suffering that led us to promises. So the goal would be to maintain the superior performance characteristics of the asynchronous model without paying this disastrous syntactic tax, or syntax. Promise time! So now that we've established our motivation, let us carefully, step by step, implement our own version of the promise. To get started, let's clear out the guts of our asynchronous program and focus on the single asynchronous call to read file. In these lines of code, there lies a dormant abstraction. What if calling read file returned some object that represented the eventual completion of reading that file, and then we could separately register callbacks for when that operation completed? This would allow us to sever the definition of this eventual book from its consumption. Another benefit of reifying this concept of an eventually resolved value is that now we have an object with methods that we might use to return other instances of that same object type, such that we can chain calls to our then method, which would allow us to solve the pernicious problem of the pyramid of doom. And we could then avoid the fate of our code being flattened against the right-hand side of our screen. There are, of course, further benefits to exploit from this structure, but let's just for now focus on the simplest example. What would it take to get something like this to work? Let me copy this and go back to our simple functioning async version, and I'll paste our ideal API beneath and comment it out. Ultimately, our abstraction will be making use of this API and will be wrapping it. So let us stumble our way through the simplest possible implementation. I'm going to define a class called eventual, which will be our version of the promise. Now we haven't yet figured out precisely how we're going to construct these, so I will simply fake the definition of an eventual book. I'll actually also quickly define a couple of little stubbing helpers so that our incomplete code is not unreadable. I'll also define one at the type level here. Okay, so we know we eventually want to construct an eventual book, and that once we have one, we should be able to chain callbacks onto it by calling .then. And therefore, our eventual class will need a then method that will accept a callback, and this will be a function whose value will be the type that the eventual class will resolve to. In this case, it's the string that will be read from the file system. And this callback will eventually be able to return a few different data types, including other eventual values or just plain values. But for now, I'll keep this as a placeholder. And of course, we want this to return another eventual value. We're not exactly sure what that should be just yet. But this is enough to make our broken program compile. So let's further think about the semantics that we want. Eventually, we're going to wrap this built-in version of read file, and we will receive the book's contents, and we're going to use those contents to complete or resolve our eventual book value. Now, there's a bit of indirection here, so let me reiterate. We will somehow construct these eventual values, which are placeholders for pending results of some type. So this would represent some in-flight computation that will eventually return a string. We should be able to register callbacks or continuations with that object, and we would want all of these callbacks to be called whenever that eventual value is resolved or completed. I'm hopeful that any confusion you have will be resolved as we actually implement this thing. The next thing to do is to stub out our resolve method. This should take the value that the eventual type should complete with, and then it should do something. Let me scroll down a little bit so we can see its usage in context. So as we just reviewed, when we call resolve with our payload, which will be a value of type A, in this case a string, we want this to execute any callbacks that were registered. So that's what we should do here. Execute our callbacks with the value. Of course, what callbacks? Now, in order for this to work, we'll first have to store the callback we receive here when then is called. So to do this, let's simply initialize a private callbacks array to hang on to them. And then we can just push onto it in then. And now that we have our callbacks captured and contained, we can then execute them one at a time when we finally call resolve. Now there are clearly some gaps in our system, these to-dos we need to take care of, but first we actually have enough to run our program here. Instead of calling to-do there, I can construct a new eventual. Let me scroll down just a little bit, and now let me run our program. And if you can see here, it actually turns out that this works. 𝓁𝓧𓅧 is being printed. This eventual data type serves as an intermediate repository for callbacks, which are then iterated through and called when that eventual book is finally resolved. Let me close this. And before fixing our stubbed out types, I do want to reveal one flaw with our current approach. Currently, we have to attach a handler before resolving. However, it is possible for our eventual book to be resolved earlier. So let me feed in a string here, comment this out, and rerun our program. Now we no longer see our red-thoth message. This callback is not being fired. Our current implementation is just a hair too simplistic. Just by glancing over the implementation, you can see that for the callbacks to fire, they must have been added to the callback array before resolve is called. But these semantics are extremely finicky and would be quite surprising to users of our API. In order to solve this problem, we will turn to types to help guide our thinking. Let's consider the possible states our little promise doppelganger can be in. When we first construct it, it will not yet have been resolved, and is thus in some kind of unresolved or pending state. And while it is pending, if we call its then method, we'll need a place to accumulate callbacks, and we'll execute these later when our eventual type is resolved. And therefore, of course, the second state we can find ourselves in is having been resolved. And in that case, we have the value that we resolved to. So now, instead of storing the callbacks, we instead want to store a state of type A, and initially this will be that pending state with an empty callbacks array. Now let's scroll down a little bit. So now we have to update both of our implementations. Instead of always having callbacks, these will only be available to us if we are in the pending state. However, it only really makes sense to call resolve on a pending promise or eventual. And therefore we can check if we are not pending, we can just return, and then we can append to our states callbacks. And then finally, the act of resolving itself should change our state to resolved, and we should store off the value that we resolved with. We'll then have access to this later on, in the case that then is called after we've already been resolved. Our current logic is fine, but only in the case that we are in the pending state. So I will wrap this, and then otherwise, we must be in the resolved state, and therefore we already have access to the value that we've been resolved with, and we can simply immediately and synchronously call our callback with the value. And oops, I need to access callbacks on our state. Now that we've made this change, let me rerun the program. And yeah, now it works again. 𝓁𝓧𓅧𓓼 is being printed out, and also this occurs before file over is printed. And this is because we resolve our promise immediately, and therefore by the time we call then, it will just directly and synchronously call our callback, passing in the value that it stored off into its state. Let me close this. And now we'll push further. Let me delete this stuff, our current example, and we want to get this previously commented out example working. So in order to do this, we need to construct a read file eventually helper method that will take a path and will return an eventual string. And then we'll do what we were doing manually before, which is construct an eventual. We will return this eventual value, and then internally we will delegate to the asynchronous read file method and resolve our eventual book just like we were doing before. If you're familiar with the actual promise API, you'll know that this is a little strange. You cannot construct a promise and then manually resolve it later on. When you construct the promise itself, it gives you the resolve function as an argument. And other than that, it's very similar. We'll still call the async read file method, but then instead of calling resolve on our eventual value, we just call the resolve that was passed into us. Under the hood, this does the same thing. It's just a slightly more limited and opinionated API. But since our overarching goal here is to perform a full Freudian psychoanalysis on the promise, we should look into its most formative experiences, which a constructor would be the closest programming analog. So let's jump up to the top of our eventual class and start to implement a constructor. The type signature here is a little convoluted, so we'll take it step by step. Let me add a little comment here to remind us of what it will look like when it's called. So what we pass in here is a function of something to void. We're not intended to return any particular value from the function that we pass into the constructor. All we're supposed to do is use this resolve function that's passed in, and when we call it, later on, that's when the underlying eventual or promise value will be resolved. Which brings us to the parameter. That is another function called resolve. And this has its own type, which is to accept the value, this a value, that should match the type of the underlying eventual, so a string in this case. And then calling this function also doesn't return any particular value. And I admit that looking at this line of code without context does make you dizzy, but hopefully stepping through that made it a little clearer. The constructor takes a function that you define, and that function is also passed as its first parameter another function that you are intended to call in your function. And we, as the owners of the eventual class, are responsible for passing in this resolve function. In fact, we will immediately call make, passing in the resolve function that we've already defined, and then we'll bind it to this, just due to JavaScript's BDSM predilections. But really, that is everything. Let's jump back down to our use site, and it now compiles. And now we can run our program again and receive another taste of sublation. And now it is time to finish this. We've left open a couple of loose ends. First, let's assign this to a const. If we look at the type, we'll see that it is an eventual of any. Even if I go down here and return the length of our text, it still shows an eventual of any. This type should be determined by the type that we return from our then function, in this case a number. The second problem is that we should be able to chain then calls. I should be able to log the length here and we should see it printed out. I could also return whether or not the length is even. Of course, this is still an eventual of any, and if we run our program, we get an error. So let's fix these issues. The problem lies in the implementation of then. We have too many to-dos. We have to-dos at the type level, and then we're finally returning a to-do. So remember that we pass in a function to then, and we store this off in our callbacks array, or call it immediately depending on the state. But we also want to be able to return any other type here. For instance, the number or the Boolean representing whether or not the length was even. And chaining on thens should return another eventual of that other type. So first we had an eventual of a string representing the text of our book. Then we turned that into a number, and then lastly into a Boolean. And right now we're returning undefined actually. What we need to do is return a new eventual value. And the easiest way to do this would be to come up here and return a new eventual of type B. And we can just wrap all of our existing logic. To help us understand, let's make this a little more concrete. In our case, A was the string of the initial text, and B would be the length, which is a number. And in order to resolve our new promise, we're going to have to call its resolve function with some B. But the only way we can get our hands on a B is by calling callback, which returns a B. However, it requires an A, so we find ourselves in a bit of a pickle. We do not have any A's in scope here. However, the callbacks array is an array of functions that will eventually be called with the A value that the original promise resolves with. So the easiest way to get this all to work is to define a new function, one that we can put into our callback array. This means it will have to take an A as its argument, and then internally we can delegate to that initial callback, passing it the value, and this will get us back our B, at which point we can resolve our new eventual B promise with that value. I'm going to claw back some more screen real estate. So now we have a new function of A to void, and we can pass this into our callbacks array instead of a callback. Or, if we are already resolved, we can just call it directly. Great. So now this should actually work. And yes, there we see the contents of our file and the length. Great. And I could even scroll down to the bottom and chain on one last section and say is even, and I won't return anything. Let's run this. So yes, we can now chain onto our promises, and it's fully type safe. As you're well aware by now, my time is running short. Yes, I can talk to fish, and I can move the moon with my mind centimeters in any direction of my choosing. But I am afraid I am fated to become a blood balloon, if what the fish tell me is true. So with that in mind, I'm going to do something I may regret, which is to copy-paste some functions I've written elsewhere. I've adapted both gzip and writefile to work with our eventual data type. And now I will paste our final challenge. If you call promises then function returning another promise, or another eventual in our case, it should actually flatten that promise. So compressed here should not be an eventual string. It should instead be the underlying string. If we can get this to work, we will have achieved our initial goal. Scrolling back up here to our implementation, we can make our last few surgical edits together. First, we will update our type signature. We should be able to return either a B or an eventual B. And now, of course, line 39 is despairing because B may not be a B, it may be an eventual B, and that would be bad. So what we'll have to do is check to see if B is an eventual value, and if so, do something. If it's not an eventual value, well then, it is indeed a B. So I stopped saying B so much, I'm going to rename this to result. And now we can see that result is known to be an eventual of B. And if we want to access the underlying value, well, we'll simply chain then onto it. And in here we can define our callback that will eventually be called with the final B value, and we can then resolve this outer eventual with that value. And that's it. I recommend carving this code into your flesh, tracing it over and over again with the blade until you understand it. And if not in this life, perhaps the next. Now let's jump back down to the bottom and see if this thing works. Firstly, it infers the correct type, which is the final Boolean. Compressed is indeed a string instead of an eventual of string. And now if we run it, we'll see what happens. And there we go. We see as it is written getting printed, and it was compressed. So we've solved the problem of callback hell and invented this new abomination. So that's it. Thanks for watching, and don't forget to like and subscribe.